So our next speaker, Mohamed, is working as a solution architect for AWS Solutions architecture team based out of Amsterdam, Netherlands. He's a subject matter expert in cloud infrastructure architecture, helping the customers scale their use of AWS safely and securely, accelerate their adoption of cloud, and driving the value of their investment in AWS, while acting as a technical liaison between customers and product teams to help evolve the AWS platform. Mohamed,
great.
All right. Hello,
will give us the
everyone.
speech
Thank
now.
you for joining my session today. My name is Mohamed Wali. I work as a solutions architect for AWS, mainly helping the enterprise and retail customers within Benelux region with their journey to the AWS cloud. And today I'm going to talk about the Amazon EKS security best practices. So this is our agenda for today. And initially, I'm going to give a quick refresher to the AWS shared responsibility model if you're not familiar with it. And from there, we're going to move forward to the container security principles. And afterwards, we'll dive deep on a big four for the security best practices. And last but not least, we're going to talk about Amazon EKS security. But pretty much everything we would cover before we had the last topic would be still EKS oriented, because eventually these containers would be running on top of Amazon EKS. So let's get started by talking about the AWS shared responsibility model. And this is actually a quick refresher for you if you're not familiar with the AWS shared responsibility model. AWS is mainly responsible for providing its services on a highly secure and controlled platform, and providing a wide array of security features that pretty much all of our customers can use. And the customer's responsibility on the other side includes configuring their IT environment in a secure and controlled manner for their own purposes. So since AWS and its customers share this kind of control over the IT environment, both parties have responsibility for managing the IT environment. AWS part in this shared responsibility model, as you see, includes providing its services on a highly secure and controlled platform, and providing a wide array of security features customers can use. And the customer's responsibility on the other side includes configuring their IT environment in a secure and controlled manner, as mentioned earlier. And while customers do not communicate their use of configurations to AWS, AWS does communicate its security and control environment relevant to customers. So AWS does this by obtaining the industry certifications and independent third-party attestations, publishing information about AWS security and control practices in white papers and websites, and providing certificates, reports, and even other documentations directly to our customers, but mainly under NDA if required. So with that, we can move to the challenges with containerized applications. So some of the challenges that we have that are different with containers is that the security model that many of us are familiar with, the virtual machine one, is actually very different than the security model of the container. And in general, the industry has accepted that the virtual machine model is a little bit stronger than the container model. So the virtual machine model is where we actually have, a separate running system with its own virtualized CPU, memory, networking, and storage. And on the other side, the container model is a little bit different, where where the security model is essentially done with the Linux kernel. So it's generally accepted that this is potentially less secure, and that there are issues with the Linux kernel that we could potentially have a security issue eventually with. And so the challenge here, ultimately, the first point is all of the processes and essentially containers are just processes running on a shared host. And anytime multiple containers running the same host, they're ultimately just Linux processes just being run on the same host using primitives such as namespaces, which essentially provide most of the security isolation, so that one process cannot really see the other process, cannot talk to another one. And then there is also a Linux primitive called cgroups, which helps you to prevent the processes from consuming too much CPU and memory, essentially provide some guardrails around that. And so this isolation is a combination of both these primitives of namespaces and secrets. One of the other kind of big changes with containerized applications is containers typically run a lot faster, a lot less than a virtual machine. So the time to live, that's actually what TTL stands for, is often much shorter. And because it's much shorter and containers are started, stopped very quickly, we need security primitives that are really able to dynamically adapt to a lot of these running systems. So the idea of having a network team that sets up a firewall around a brand new virtual machine that's provisioned for an application is not really the same type of security model where containers can be created on the fly. And so we need security primitives and security models that are able to react to these dynamics and changing workloads. And that's what the next 2 points are also mainly about. So the next item here, the say traditional legacy software typically is not container aware. And there are a lot of them that are indeed not container aware, but on the other side, they are trying to enhance and modernize, becoming more container aware. And when we talk about, how we actually provide security controls, detective controls to both prevent malicious actors, malicious content, and restrict container both for runtime and images from being able to do more than they should, all of these kind of conversations, we are still a bit behind when having very decent solutions from the legacy ones to really help us achieve so. So I guess the whole point here is that container-based security is a completely different approach than the virtual machine one, or what we can traditionally consider an EC2-based based security. So you want to be able also to provide some security protection across many different layers when it comes to working with containers. And I like to think of it as there is this big four, and those big four items are the container supply chain. So some of that comes into image protection, source code, essentially everything that goes through from a developer creating a container all the way to producing a container image. The second item is host-based security, so that would kind of fall in maybe this top area here. Another one would be runtime-based security. So let's say that that's number three. And so that might fall into some of this container and configuration. And number four would be the network security part. So those are kind of the big four, and I'll kind of walk you through them. And again, the first one of being focused around container images and supply chain, host-based security, runtime security, network security. And we are actually going to walk through pretty much all of them throughout our presentation today. So let's get started by the container security best practices. And that's where we're going to actually focus on the big four that I was just talking about, starting from the supply chain security, host security, runtime security, and ending it up with network security. So container security supply chain. So the first one here would fall into my top four items as supply chain. And this talks through a number of the container images, image security best practices. And again, I'll kind of walk you through these as we go through all of the best practices. And many of the security controls require changing processes, changing the way you create an image, the way you manage containers, and you may not have controls. So you might want to ask yourself some questions such as, is my team ready to do that? It may be that they could do it, but then operationally there are different teams and you have to be educated eventually. So there is a lot of times security becomes an evaluation where they are always working towards implementing more and more of these. So the first one of the container image security best practice is to create minimal images. And the purpose of creating minimal images is to reduce the attack surface primarily if there is a vulnerability. So if there is some sort of issues, even if we see all the time that there are many libraries that have vulnerabilities, and if we can avoid that library that's not needed in the container, in addition to reducing the number of layers and image, and you can achieve that with tools such as Docker Slim, which is a tool that provides a set of commands such as build, X-ray, lint, and others in order to simplify and optimize your developer experience with containers. It makes your containers better, smaller, and more secure. It's also highly recommended as well to use a minimal base image. So a best practice for a container image is that it should be focused on a single item. So it has a single concern to be self-contained. And the reason why we want a minimal based image is that the initial based images usually start with contain a number of components that that were very similar to distribution flakes. And the reason that was there is that most applications would depend on like the FCD file system or binaries in SPIN or maybe some very common libraries. And so for maximum compatibilities, we had base images that were based on particular distributions, typically the distribution that you were familiar with running. The challenge was that is that now you have a larger attack surface, and so there may be binaries that we don't really need at the runtime, and they have to be removed. And one of the most important one of these is the shell environment, and that just means it removes another attack factor of someone being able to do that, to be able to actually execute a shell or potentially throw privilege escalation, run a shell, and then run other commands inside the container. The most common question that comes up is, if I remove shell troubleshooting, all right, how do I debug? So for that, you can use Kubernetes ephemeral containers, which will enable you to troubleshoot pods by deploying a temporary debugging container. And it's available in beta as of version 1.23. And a good example of the minimal base images that you can use is Scratch or Distroless. In case you're not familiar with none of those, Scratch is a container image with literally nothing in it, and Distroless is a very, very, very small image. On the other side, we also need to think about the multi-stage builds because multi-stage builds can make using these minimal-based images more easier, as it allows you to have the first part of the build where you could potentially use an entire, let's say, Go as a runtime and that has all of the components that to actually build and compile. And then as soon as I have that output, which is my Go binary, the next stage of the build is I can now bring in my Scratch image, for example, and then only produce a container that's built with Scratch with no other components. Another best practice that you should consider is signing the container images, because it will help you to provide you with a means to validate where a container image is coming from, checking that the image has not been tampered with, setting policies to determine which validated images you will allow to be pulled to your systems, and so on. So you should. So it's quite important. Unfortunately, not too many customers are using it. Maybe because it's not pretty straightforward, but it is definitely a good one. You should also be linting your Docker files as well. So where the linter would help you to build a secure Docker image eventually, that applies best practices. And a good example for the linters that you can potentially use is something like Docker and Hadolint. Besides that, you need to defang your containers, but how you can do it? By just removing the CQID and CGRD flags on binary executables, which allow users, to run an executable with the file system permissions of the executable's owner or group, respectively, and to change behavior in directories. And you really don't want to have that in your environment. And you also need to perform some static code analysis and start application security testing for your images before deploying them generally, in order to detect if the image has any vulnerabilities, and that should be in an earlier stage in your pipeline before the actual deployment to your environments. And I'll touch on the tools that we can use in order to achieve that later on. The last slide for the container image security best practice here contains also another 3 best practices that should be there. The first one is you should never have any sensitive data in a container, and a container should only have all of its configuration along with all of its secrets injected at runtime. Also, if you're building apps on containers, you have more than likely heard about the 12 factor. If you didn't, then simply the 12 factor principles provide a well-defined set of guidelines for developing microservices. And the assertion is that by following these practices, you will be able to easily run, scale, and deploy your applications or microservices. And last but not least, immutable tags are very, very, very important in the security process. And let me explain why. So if you use a tag, and it could be, we definitely want to avoid tags like dev or prod, because those would be something that's pushed all the time and you have no idea what version you're running. Let's say we have a tag that has a name of the application version, let's say 1.0.2. Maybe even a build hash commit on there, So if you don't have an immutable tag, a malicious actor can really has access to that really has access to your registry code, push a brand new image with the same exact tag over top of it. And then transparently, as your application run and deploy, they would now be pulling a malicious image. So simply immutable tags is something that's really, really important for security, as you have seen. But what can you use for storing your tags? A good example of it is Amazon Elastic Container Registry. It's similar to Docker Hub, but ECR would enable you to implement many of the best practices that we have just discussed. And you can configure an ECR repository to be immutable to prevent image tags from being overwritten. You can also manually scan container images stored on Amazon ECR. Alternatively, you can configure your repositories to scan images when you push them to a repository. And Amazon ECR uses the common vulnerabilities and exposures, the CVEs database, from the open source Clear project and provides a list of scan findings. That's in case you're using Clear for image scanning, but you can also use Amazon Inspector, and I will touch on pretty much both of them later on. So based on the findings, also Amazon ECR would send an event to Amazon Event Bridge when an image scan is completed. So you can leverage this to send alerts about whether an image scan completed clean or detected any vulnerabilities. And you need also to think about your ECR lifecycle policy that contains, one or more roles where each role defines an action for Amazon ECR. This provides you with a way to automate the cleaning up of unused images. For example, expiring images based on age or count. And of course, you can also expose your ECR repositories via the VPC interface endpoints, which simply would enable you to use the backbone network of AWS to hit them instead of going through the public internet to your EKS if you run it on AWS. And that's also a very important one to be done in place. And you can definitely restrict access to your ECR repo by making sure that the IAM policy is assigned to pretty much everyone, and to it also is restricting the access to only the other services that would really need to reach it out, or the other roles that really need to access it. And of course, you can utilize cross-region replication. It's not really a big security one here, but it's more, just in case you had some severe problems in one region for any natural disasters that might happen anytime, maybe you would need to get it, if you're replicating it to another region, you can really have your environment up and running right away. So we talked in the previous slide about some image scanning tools such as Claire. And Claire is an open source project for the static analysis of vulnerabilities in application containers that currently, I think, include OCI and Docker as well. So, if you're using the Claire API to index your container images, you can then match it against the known vulnerabilities, as I talked about it earlier, and the flow of the scanning process, would look like something as you see here in the diagram. So first you as a client will initially push the image to the ECR registry, and then ECR will then scan the images operating system and returns the scanning results in ECR. And finally, it will repeat the process every time a new image is pushed. But how it also would look like with Amazon Inspector. So if you're not familiar with Amazon Inspector, it's simply an automated vulnerability management service that continually scans AWS workloads for software vulnerabilities and unintended network exposure. So the scanning process for Amazon Inspector will be something also, as you see here in the diagram. First off, the client, will initially push the image to the ECR registry. Then Amazon Inspector will scan the images always and the programming language packages. And if Amazon Inspector got any findings, it will prioritize them and sends to AWS Security Hub if it is enabled in your environment. And finally, it will continuously scan the image and will go through the same process for a newly pushed image as well. And with that, we can wrap it actually for the supply chain section, and we can now move to the container security from the host perspective. So your Kubernetes host should be optimized for containers in order to minimize the service attack. And for that, we offer some ready-to-use images you can use, such as EKS optimized Amazon Linux 2 image or BottleRocket. BottleRocket is actually a Linux distribution sponsored and supported by AWS, and it is purposely built for hosting container workloads. So it includes only the essential software to run containers, which improves resource usage, reduces security attack surface, and lowers the management overhead eventually. Besides that, there is also general best practice, to run on private subnets. That's just because if we run on public subnets, we potentially expose the node directly to the internet, and it's less of a concern. So of course, if you have a security group in place where you're only accessing the application, but still, it's just a little bit of a more risk if you're running on public. Also restricting the access to your host by removing SSH access and need for key pairs and enable auditing to be able to track any API access or malicious operation is quite important as well. And for accessing, you can definitely utilize AWS Systems Manager Session Manager in order to access your host without having to open any ports or using any key pairs. And earlier on, we talked about Amazon Inspector for scanning images, but it can also be scanned operating systems as well. So for software vulnerabilities and unintended network exposure. So utilize that for your host as well. And you should be continually assessing your hosts against CIS benchmarks. And you can do so by using KubeBench, which can evaluate your cluster if it's CIS compliant or not. And in case you're running Red Hat or CentOS as operating system of your host, just make sure to use SE Linux as it provides an additional layer of security for your system. You can also block the use of the instance metadata service to bots, and that's a very important one as well. But let me give you an idea of IMDS if you're not familiar with it. It's simply the data that's related to an Amazon EC2 instance and where your applications can use to configure or manage the running instance. So the instance metadata service is simply an on-instance component that code on the instance uses to securely access instance metadata. And you can use it, for example, in order to retrieve some secrets that temporary credentials, for example, that are coming out of an IAM profile associated with this instance. And you can restrict that either by the network policy that can be used to selectively allow metadata access to the pods, or via the launch template of the EC2 instance itself, where you can also set token hop limit. When it comes to encryption, it's also a very important topic for your storage. So you can use AWS KMS, which is a key encryption service, to encrypt pretty much all of your storage for Amazon EKS. And should be treating your worker nodes all the time as immutable. If you ever want to patch a node, upgrade Kubernetes, treat this as immutable and create a brand new one, especially like a host replacement versus performing any sort of mutations like, utilizing Puppet or Chef or AWS SSM, one of AWS SSM solution that can help to do this automation for you. So just recreate it with a totally new configuration and replace your existing one. And last but not least, use tools such as Secomp and AppArmor to monitor and control your syscalls. And if you're not familiar with Secomp and AppArmor, Secomp would help you to reduce the chance that a kernel vulnerability would be successfully exploited, and AppArmor would prevent an application from accessing files it shouldn't have access to. And with that, we also have wrapped up the part of securing the host. Now, we are going to move to securing the runtime part. We are going to get started by talking about limiting container resources. And I know limiting container resources is not really, super security item, but I would consider this, to be like a denial of service security, right? So you only provide the resources each container needs for normal operations so that root containers cannot really consume all the resources and cause downtime for them eventually. And one of the best practices here is always to not run privileged containers and not to run its root. So you may be aware that by default, all the containers that will run would be using root. So if you do nothing, and in fact, I can see many container images that are not really doing anything and running just as root. There is a phenomenal amount of work I know that is necessary to have a major application not using root, but it's really worth it from a security perspective, because if the container is running in privileged mode, the unauthorized user or malicious actor could obtain host level access, and this could compromise not only the host itself but also the control plane. And this pretty much means game over. So you really should consider investing some effort in that. You should also avoid running host path if possible. Of course, empty directory is okay, but if you have host path, you're now essentially breaking through the secure storage boundary of the container and allowing access to host-based storage, and we want to avoid that at all possible. There are and have been way too many directory traversal attacks in applications, and if one were to exist and one were to be found, and someone has access to a container and now can potentially get access to a pass on the host, we will definitely want to avoid that, but we also want to restrict host networking. Technically, what this does is this breaks out of the networking namespace and allows access to host networking. And one of the biggest issues with having access to host networking is now you have access to all of the IAM roles and principal rights that are assigned to the EC2 instance, because you can just access the metadata and get access to the host-based roles. And that's why earlier also talked about disabling the instance metadata to avoid similar situations. And also earlier on, when we talked about the need for automated security, compliance, and privacy controls that detect, prevent, reduce, and also counteract known and unknown threats, that has been heavily increasing in the last few years. And out of this increased need for controls, policy as code solutions have emerged to meet these demands. And there are several policy as code solutions available in the open source software community, such as OPA, which is an open source general purpose policy engine that can be used to enforce policies in Kubernetes. And before that, for a while, we used to use a feature called pod security policies, or PSP, which was very powerful actually, but it was also could be extremely difficult to use, and they are set for deprecation now. So in a nutshell, policy as code solutions can manage all Kubernetes resources. And that takes us to the last one and the big four security best practice, which is networking. So let's take a look now at the encryption in transit for Amazon EKS, for example. So there are multiple different options for network encryption. So by using service mesh, such as AWS App Mesh, and using App Mesh, you can configure all traffic between Envoy proxies to be encrypted using TLS certificates, either from a private CA or from AWS Certificate Manager. If you're using Nitro instances, for example, the traffic would be automatically encrypted between most of the instance types. And if you're using load balancers with TLS certificates, this means that the traffic will be encrypted to the load balancer, but will be unclear between the load balancer and the pod or the container that's trying to reach out. And this is supported for both application load balancer and the network load balancer. And finally, you can do the encryption or decryption in the container itself by deploying a TLS certificate with a container. And you could use a secret, to reference the certificate or mount a shared volume that can hold the certificate, which is accessed by the containers needing the encryption. You can also achieve bot-to-bot communication security by either using security groups, where you can incorporate EC2 security groups with Kubernetes bots, or you can use network policies, which is Kubernetes native approach for traffic control that will help you implement network segmentation and tenant isolation. And in the upcoming slides, I will discuss both of them in more details. So starting off with security groups. Before security groups for pods, you could only assign security groups at the node level, and every pod on a node shared the same security group. So to work around this limitation, you had to spin up separate node groups per application and configure complicated taint and affinity rules to schedule pods onto the right nodes. And this is difficult to manage, especially at scale. So Kubernetes network policies provide an option for controlling network traffic within the cluster, but do not support controlling access to AWS resources outside the cluster. So network policy rules that span pod to pod and pod to external AWS service traffic can be defined in a single place with EC2 security groups and applied to applications with Kubernetes native APIs. And after applying security groups at the pod level, your application and node group architecture has to be simplified as you see here. So you need to enable pods to get their own network interfaces, and this is a trunk and a branch ENI set up on the node. And then you can apply your security group to a service account using a security group policy. And security group policy simply is a namespace code custom resource definition. So it applies to pods within a specific namespace, and it uses the Kubernetes magic to do this via mutating the webhooks. But one important one to notice here, you cannot really combine a security group for pods and network policies. The security group for pods are limited to a specific number of interfaces per instance type. So it should be used with workloads that are required to be isolated using specific security group. And to talk a bit about, the security groups for pod architecture, on the previous slide, I talked about the ENI trunking. It's simply a feature that allows, for many network interfaces known as branch ENI from various VPCs to be multiplexed through a single ENI, aka trunk ENI, attached to an instance. And this would allow for greater scaling of multiple customers on a single instance for Amazon provided services. And it is currently supported on most of the recent instance families based on AWS Nitro hypervisor. And it is compatible, this approach is compatible with custom networking, but it ignores the security group in the ENI config. So network policies, we've been talking about it for some time. What it is actually. So network policies are a set of rules that enable you to restrict communication between pods or between pods and resources outside of the cluster. And this can be used as an alternative to AWS security group to secure network traffic between pods and implement network segmentation and tenant isolation. Unlike security groups, though, which are assigned to the ENIs, you assign network policies to pods by using pod selectors and labels. Network policies are implemented by the CNI plugin, but the VPC CNI plugin doesn't have its own policy engine. Therefore, you will have to use a policy engine such as Calco to support network policies in EKS. And by default, pods are non-isolated, so they accept traffic from any source from within or outside the cluster. Pods become isolated by having a network policy that selects them. So network policy would be a namespace scoped resource. Once there is any policy in a namespace selecting a particular pod, that pod would reject, any connections that are not allowed by that policy. And other pods in the namespace that are not selected by any network policy would continue to accept all traffic. And those are the fundamental rules regarding how network policies implement traffic control. And that takes us to the last section of the session, which is about Amazon EKS security. So far we have been really going through container security best practice, but they relate to EKS eventually. So that's why I will not really have to repeat them and go through them again within this section. So earlier when we talked about the AWS shared responsibility model, I can dive a bit deeper to show you how the EKS shared responsibility model would look like. So if you're using EKS with self-managed workers, when you're running workloads in your own EC2 instances, you would be responsible here for pretty much everything on the data plane. That includes OS patching, node scaling, etc. So the blue side is totally managed by AWS, but the orange one is yours to manage. If you're using EKS with managed node groups, though, some of that responsibility shifts a little bit over to AWS when you use managed worker nodes. So when managed nodes run an EKS optimized AMI, EKS would be responsible for building patched version of the AMI when bugs or issues are reported. We can publish a fix, however, you still would be responsible for deploying these patched AMI versions to your managed node groups. And when the managed node groups run a custom AMI, you would be actually responsible for building the patched version of the AMI when a bug or issue are reported and then deploying the AMI to your cluster. And with Fargate, which is actually the serverless version of Kubernetes on AWS, if you're running it, EKS on AWS Fargate, all the aspects of maintaining the worker node security shifts to AWS, as you see here. So with that, let's focus on some of the key best practices for EKS, starting from the client authentication and authorization. So EKS currently supports 3 types of authentication, such as service account authentication, IAM authentication, and OIDC identity provider authentication, and I will cover them shortly. When it comes to authentication, EKS relies on the native Kubernetes role-based access control for authorization. So role-based access control is a method of regulating access, normally to a computer or network resources, based on the roles of the individual users within your organization that would allow you to dynamically configure policies through the Kubernetes API. So let's see the first option, how we can manage external access via IAM. So as you see here, users have an IAM permission policy that allows them to assume the IAM role. Let's call it, for example, an EKS developer role. So starting from the user that would authenticate it, assumes a role, then it would search for this role on the AWS auth config map, which simply where we can map the IAM role to a Kubernetes role-based access control user or a role. And to see an example of it, we can have a look at this example. So AWS auth config map is simply would enable you to map an IAM role to a Kubernetes subject. And there are 2 types of Kubernetes subjects, could be users, could be groups. And here we are mapping the IAM role named EKS developer role to a Kubernetes group named developers. And when you have any external client such as kubectl to interact with EKS, it has to pass an authentication token in the request that's sent to the API server. And the client-side component called IAM Authenticator is mainly used here to generate this token using the credentials of an IAM user for the role or the role. And on the server side, EKS interacts. There is a component called token authentication webhook with IAM to verify if the authentication token is valid. And once authentication is successful, the Kubernetes role-based access control system is used to grant a set of permissions to the client. And OIDC authentication was also something that many customers demanded from us. That's why we started support it less than 2 years ago so far. And now you would have the flexibility to use an OIDC compatible IDP of your choice. And this would give you a Kubernetes native way to grant your users access to EKS clusters using an OIDC compatible identity provider. Simply, OIDC authentication is a well understood concept. There are several options available for making kubectl fetch an ID token from an OIDC identity provider. And you can use something as simple of kube login. Another option is DIX, which acts as a portal to other identity providers such as LDAP through connector. And DIX runs natively on top of any Kubernetes cluster. And additionally, you just need to configure your EKS cluster with information about the OIDC identity provider you're using. That leaves us with service accounts, and simply service account is an automatically enabled authenticator that uses signed bearer tokens to verify requests. They are typically used to provide an identity for a pod, but the service account bearer tokens are perfectly valid to use outside the cluster as well in order to talk to Kubernetes APIs. IAM rules for service accounts can help you to scope IAM permissions to a service account, and only pods that use that service account have access to those permissions and eventually achieving a least privilege for bots. Also, a pod's containers can only retrieve credential for the IAM rule that's associated with the service account that the container uses. A container never has access to credentials that are used by the other containers in other pods. And that leads us to the analyze control plane logs, which are quite important as well, since EKS control plane logging provides audit and diagnostic logs directly from the Amazon EKS control plane to CloudWatch logs in your own account. And these logs makes it easy for you to secure and run your clusters. You can actually start using EKS control plane logging by choosing which log types you want to enable for each new or existing EKS clusters. And there are 5 different log types available, and each log type corresponds to a component of the Kubernetes control plane, such as API server, scheduler, authenticator, etc. An API server logs tells you about all API access to your cluster. So audit logs provide a record of the individual users, administrators, or system components that have affected your cluster state. Authenticator logs, for example, are also unique to the Amazon EKS. These logs represent the control plane component that the Amazon EKS uses for authentication using IAM credentials. And generally speaking, all these logs can be analyzed using CloudWatch log insights to monitor and identify your cluster activity against security threats and create a governance framework for security best practices. And last but not least, Amazon GuardDuty can be used for protecting your Amazon EKS. So GuardDuty EKS protection would enable Amazon GuardDuty to detect suspicious activities and potential compromises of your clusters within the Amazon EKS. And EKS protection is an optional enhancement that enables GuardDuty to consume Kubernetes data sources. And the process for enabling or disabling GuardDuty EKS protection is covered in this part. So we strongly recommend that you do not disable EKS protection in GuardDuty. If the feature is not enabled, the ability of GuardDuty to monitor or generate findings for suspicious activity within your Amazon EKS environment would be actually limited. Now with that, I really would like to wrap up the session over here. I hope you have enjoyed it and find it insightful, and I wish you a nice day ahead. Thank you.
Okay.